Hello my friends and welcome back to the You Can Do TV channel. La Nouvelle Route du Littoral is a large-scale marine infrastructure project engineered to replace an obsolete and high-risk coastal roadway on Reunion Island. The primary technical objective is to deliver a permanent, all-weather transport corridor capable of withstanding extreme ocean, geological, and climatic conditions while maintaining uninterrupted traffic flow. The project extends over 12.5 kilometers and is composed of two distinct structural systems, offshore viaducts and heavy marine dikes. This hybrid design was selected to balance constructability, durability, and environmental constraints along a coastline characterized by deep water, strong swells, and unstable volcanic cliffs. The viaduct system represents the most technically complex component. The main offshore viaduct requires 48 reinforced concrete piers, each founded directly on the seabed. Due to water depth and exposure, conventional in-situ construction was not feasible. Instead, the project relies on large-scale prefabrication, offshore heavy lifting, and precision placement. Pier elements are produced in a dedicated port-based precasting facility. The lower pier bases weigh up to 1,800 tons while the upper pier heads reach 2,300 tons. These elements are cast using high-performance marine-grade concrete, designed for long-term resistance to chloride penetration, wave impact, and cyclic loading. Strict quality control ensures dimensional accuracy, surface durability, and structural integrity prior to transport. Transportation and installation are carried out using Zurite, a purpose-built self-elevating jack-up barge. Equipped with multiple stabilizing legs and a 5,000-ton lifting capacity, Zurite allows entire pier segments to be installed in a single offshore operation. Once positioned, the barge elevates itself above sea level, providing a stable platform for vertical placement and seabed fixation. This method significantly reduces offshore construction time and limits environmental disturbance. Following pier installation, the bridge deck is assembled using precast voussoirs. A total of 386 deck segments are manufactured in a second onshore factory using adjustable formwork systems. Segment heights vary from 7 meters near the piers to 3.8 meters at mid-span, accommodating changing structural demands along the span. Deck construction is executed using the balanced cantilever method, where segments are installed symmetrically on either side of each pier. This technique maintains structural equilibrium throughout construction and eliminates the need for temporary marine falsework. Once segments are placed, they are connected using post-tensioning tendons, forming a continuous pre-stressed concrete box girder. Inside the deck, a central hollow box provides both structural efficiency and long-term access. Pre-stressing cables act as the primary load-bearing system, distributing forces toward the piers. Internal inspection corridors allow for future monitoring, maintenance, and potential cable replacement, extending the service life of the structure. Parallel to the viaduct, the coastal dike sections form a second major engineering system. These dikes are constructed from layered rockfill and armored with prefabricated concrete blocks, including acropodes and X-blocks. The armor layer is intentionally porous, allowing wave energy to dissipate gradually rather than reflect, reducing structural stress. Block placement follows a precisely engineered geometry. Individual units, weighing several tons, are positioned by crane using GPS-assisted systems and underwater placement technology, eliminating the need for diver intervention. The interlocking behavior of the blocks ensures overall stability, even if localized displacement occurs under extreme wave loading. From a technical standpoint, La Nouvelle Route du Littoral is a convergence of industrial prefabrication, offshore heavy lifting, pre-stressed concrete engineering, and marine geotechnics. Designed for durability, resilience, and maintainability, the project establishes a new benchmark for large-scale coastal infrastructure in high-risk marine environments. Once completed, the route will provide a structurally robust and operationally secure transport access, engineered not only to meet present demands, but to withstand the environmental realities of the coming decades. The Walterdale Bridge in Edmonton, Canada represents a landmark achievement in long-span bridge engineering. The structure spans 216 meters and rises 54 meters above the North Saskatchewan River, defined by its iconic steel arches. A critical construction phase involved the precise assembly of the arches on land, followed by controlled dredging of the riverbed to enable flotation. Once buoyant, the massive arches were carefully maneuvered into position using synchronized marine operations, ensuring geometric accuracy and structural stability. Throughout excavation and construction, extensive consultation was carried out with 21 Indigenous communities who continued to monitor the works to protect cultural and environmental interests. The river arch float operation demonstrated advanced coordination between structural engineering, hydrology, and construction logistics, resulting in a bridge that combines technical performance, cultural respect, and architectural distinction. The first arch lift of the Walterdale Bridge represented one of the most demanding stages of construction. The steel arch section, weighing approximately 950 tons, was lifted 15 meters in a highly coordinated operation. Specialized hydraulic lifting systems worked in synchronization to control load distribution, movement speed, and structural stability throughout the process. Continuous monitoring of alignment, stress levels, and environmental conditions ensured precise positioning and operational safety. The entire lift was successfully completed in just 6 hours, demonstrating exceptional planning, advanced heavy lift technology, and disciplined execution under strict engineering tolerances. The Walterdale Bridge second arch lift marked a decisive milestone in the project's structural assembly. The steel arch, weighing approximately 200 tons and spanning 150 meters, was raised in a carefully controlled operation. Hydraulic jacking systems and synchronized lifting equipment elevated the arch by 20 meters, ensuring uniform load distribution and precise alignment with the completed supports. Continuous monitoring of stresses, geometry, and wind conditions was maintained throughout the lift to guarantee safety and accuracy. Once positioned, the arch reached its final height of 54 meters, completing the defining structural element of the bridge. This operation demonstrated advanced heavy lift engineering, meticulous planning, and high-precision execution under demanding conditions. The installation of a 72-inch reinforced concrete pipe, RCP double-barrel storm drain, represents a major underground infrastructure operation requiring precision, coordination, and heavy-duty equipment. A CAT 365 hydraulic excavator is deployed as the primary lifting and placement machine. With its high lifting capacity and stable operating envelope, the excavator safely handles each 72-inch RCP section, positioning the pipes with controlled movements to prevent joint damage or misalignment. Proper rigging techniques are applied to maintain balance and protect the pipe ends during lifting. Pipe bedding is carefully graded and compacted to provide uniform support along the full barrel length. Each pipe section is then lowered into place, aligned horizontally and vertically, and joined using gasketed bell and spigot connections to ensure watertight performance. Once both barrels are set, joint integrity is checked before backfilling begins. Selected fill material is placed in controlled layers and compacted evenly on both sides to avoid differential loading. When completed, the double 72-inch RCP system provides high-capacity stormwater conveyance, enhanced redundancy, and long-term durability for demanding drainage applications. Diaphragm wall construction is a critical foundation technique, widely used for deep basements, underground structures, and major infrastructure projects, where ground stability and water tightness are essential. The operation begins with boring. Specialized trench cutters or hydraulic grabs excavate the soil in predefined panels to the required depth and alignment. Throughout excavation, bentonite or polymer slurry is continuously circulated to stabilize the trench walls, prevent collapse, and control groundwater inflow. Verticality, panel geometry, and excavation depth are monitored in real time using precise surveying and control systems. Once excavation reaches the design depth, reinforcement installation follows. Prefabricated steel reinforcement cages are assembled according to structural drawings, ensuring correct bar spacing, lap lengths, and concrete cover. The cages are carefully lowered into the slurry-filled trench using cranes, maintaining alignment and avoiding contact with trench walls to preserve stability and accuracy. The next stage involves installing the stop end. This temporary formwork element defines the boundary between adjacent panels and ensures clean, well-aligned joints. Stop ends are essential for maintaining continuity between panels and for achieving the required load transfer and watertight performance of the completed diaphragm wall. The final stage is concreting, carried out using the Tremie method. Concrete is placed from the bottom of the trench upward through Tremie pipes, ensuring a continuous, uninterrupted pour. The I-57 road construction project near Mount Vernon, Illinois, represents a comprehensive highway widening and resurfacing operation designed to improve traffic capacity, safety, and long-term pavement performance. The scope of work involved widening a 4-mile segment of Interstate 57 from 2 lanes to 3 lanes in each direction, addressing growing traffic volumes on this critical regional corridor. Construction activities were scheduled for completion in December 2013 and executed while maintaining traffic flow through carefully phased work zones. The resurfacing process began with detailed site preparation and subgrade evaluation to ensure structural integrity. Once the base conditions were verified, crews installed chairs and reinforcing steel, rebar, to provide tensile strength and control cracking in the concrete pavement. Precise spacing and elevation of the reinforcement were critical to achieving uniform load distribution and long service life under heavy vehicular traffic. Concrete production was carried out using controlled batching procedures to meet strict performance specifications. Aggregate, cement, water, and admixtures were proportioned to achieve the required strength, workability, and durability for interstate highway use. The concrete was then transported to the site by a continuous fleet of mixer trucks, ensuring a consistent supply and minimizing interruptions during placement. At the paving front, concrete was discharged directly onto the prepared roadway and spread evenly across the lane width. Slip-form paving equipment established the pavement profile, thickness, and cross-slope, while vibration systems consolidated the concrete to eliminate voids and ensure proper bonding around the reinforcement. The paving operation relied on a Gomaco GP 2400 4-track concrete slip-form paver, a high-production machine capable of placing wide pavement sections with exceptional accuracy. The tracked configuration provided superior stability and traction, allowing the paver to maintain consistent line and grade while handling large concrete volumes. Skilled crews followed closely behind, performing hand finishing along edges, joints, and transitions where precision was essential. Jointing operations were executed at predetermined intervals to control shrinkage cracking and accommodate thermal movement. Surface texturing was applied to enhance skid resistance and improve vehicle safety under wet conditions. Throughout construction, quality control testing was conducted on-site, including slump tests, air content measurements, and compressive strength sampling. These checks ensured compliance with design standards and provided confidence in the durability of the finished pavement. completed I-57 widening project delivered a smoother, stronger, and more efficient roadway. By expanding capacity and upgrading pavement structure, the project enhanced traffic flow, reduced congestion, and extended the service life of this vital interstate route, demonstrating the precision and coordination required for large-scale concrete highway construction.
Paving slabs are widely used for pedestrian areas, courtyards, and landscaping projects, and their durability depends directly on proper installation methods. The installation process begins with site marking to establish reference levels and paving heights. Topsoil is excavated, and the area is backfilled with a compacted sand layer. Over this base, a geotextile membrane with a density of 150 grams per square meter is placed to stabilize the structure and protect against fluctuations in groundwater. Along the perimeter, curbstones are installed to define boundaries and prevent slab displacement. A base course of granite crushed stone, 20 to 40 millimeters fraction, is evenly spread, leveled, and compacted using a vibrating plate. A secondary layer of finer crushed stone, 5 to 10 millimeters, is then applied and compacted in stages to achieve a dense and stable foundation. A leveling layer of fine aggregate is distributed, aligned by guide rails, and compacted. Paving slabs are placed according to the chosen design pattern. Joints are filled with dry sieved quartz sand, ensuring full depth penetration. Finally, the surface is compacted with a vibrating plate through a rubber pad to align slabs evenly. Following these steps provides a uniform, long-lasting surface with high strength and an aesthetically pleasing appearance. Paving slabs are an integral part of modern urban and landscape design, combining durability with visual appeal. BRAER is recognized as a leading producer of vibro-pressed paving slabs, using advanced technology to achieve strength, precision, and decorative variety. The slabs are manufactured as two-layer composites, a gray structural base and a colored facing layer known as color mix. The base provides mechanical strength, while the facing layer delivers aesthetic value. Both layers are inseparably bonded during the production process. Raw materials, including river sands and dark granite aggregates, arrive at the plant and are stored in sectional hoppers. A conveyor and reversible transporter distribute each component into its dedicated bin. A weighing trolley collects exact portions according to the production recipe, ensuring precise batching. The mixture is lifted by skip hoist to the mixer, where cement and water are added. Intensive mixing produces dense gray concrete, which is then directed toward the forming zone. In parallel, the facing layer is prepared. Light quartz sands are combined with mineral pigments to achieve a wide spectrum of colors. These ingredients are batched with similar precision, lifted to a separate mixer, and blended with cement and water to form decorative concrete. The press forms the two-layer slab. First, the mold matrix is filled with the gray concrete base and lightly pre-pressed. Next, the colored facing mix is added. The punch and matrix then apply synchronized vibration and pressure, creating dense compaction and excellent adhesion between layers. Once pressed, separation of the layers becomes impossible, ensuring both strength and long-term surface quality. Fresh products are transferred to curing chambers designed as thermal insulated enclosures. During hydration, cement generates heat, naturally raising the internal temperature to around 40 degrees Celsius. This environment accelerates early strength gain, allowing slabs to reach handling strength within 16 hours. Mechanical properties are tested in the plant's laboratory, where slabs demonstrate resistance to loads up to 75 tons. In addition to mechanical testing, human inspectors evaluate surface quality, color consistency, and overall appearance. Any product not meeting standards is replaced before packaging. Finished slabs are carefully stacked with non-woven separators, wrapped in protective film, labeled, and transported to the warehouse. From there, products are distributed to customers. Brayer paving slabs combine structural strength, frost resistance, and long service life with attractive color and texture. Advanced production control ensures reliability in both public infrastructure and private projects, making these slabs a benchmark for quality and durability in the paving industry. The Viaducts Megablock is a high-performance concrete vibropress designed for large-scale production of paving stones, wall blocks, and special concrete products. It features advanced dual-layer molding capabilities with a color-mixed top layer, enabling the creation of aesthetically appealing surfaces while maintaining structural integrity. The minimum height of molded tiles is 25 mm, and the press can handle products up to 400 mm in height, offering versatility across multiple construction applications. Raw materials are fed into the machine and distributed evenly into molds, ranging from 1,200 by 1,200 mm to 1,500 by 1,500 mm. 8 servo-driven vibrators, arranged across 2 independent vibrating tables, provide precise frequency, amplitude, and phase control. This ensures uniform compaction and high-density products. 2 hydraulic motors of 45 kilowatts each supply the pressing force, while a total of 120 kilowatts from the servo motors drives the vibration system. The combination of pressing and synchronized vibration produces high-quality blocks and tiles with minimal defects. After molding, panels and blocks are transferred via an automated finger car system to curing areas or stacking conveyors. Optional electronic or pneumatic palletizers streamline the handling of large batches, improving productivity and reducing manual labor. The press cycle time ranges from 12 to 16 seconds, allowing output rates of 4,500 concrete blocks per hour, or 330 to 370 square meters of single-layer paving per hour. The Mega Block also supports dual-layer production, with textured and colored surfaces for enhanced durability and visual appeal. Vent holes in the mold prevent air entrapment and ensure full compaction, while digital displays confirm program settings for consistent quality control. After curing, products can be fitted with protective membranes or labeled for dispatch using fully automated systems. Investing in a Viaducts Megablock offers multiple benefits: increased productivity, reduced labor costs, precise quality control, and the flexibility to produce a variety of concrete products. Its combination of servo vibration technology, hydraulic pressing, and automated handling makes it ideal for modern concrete manufacturing facilities seeking efficiency, reliability, and high-quality output. With a minimum factory space of 2,000 square meters, the Megablock integrates seamlessly into production lines, meeting the demands of large-scale construction projects. The Vybor SPB Semsis plant, part of CSS Company, is one of the largest manufacturers of vibropressed concrete products in northwest Russia. The production of paving slabs follows a fully automated, strictly controlled process designed to ensure consistent quality and durability. Raw materials, cement, sand, crushed stone screenings and additives arrive by road or rail and undergo preliminary preparation, including fractioning, sieving, and heating in cold seasons. The plant operates its own certified laboratory, which performs incoming quality control of all components. Prepared materials are transported to storage bins of the mixing unit. Concrete batching is carried out automatically according to preset recipes. Conveyors feed the components into the mixer, where they are homogenized under electronic control. The fresh mixture is then transferred by belt conveyor to the press machine. Vibro-compression technology, combining vibration and high pressure, ensures dense compaction and precise geometry of each product. Immediately after demolding, the green products are inspected for geometry, density, and surface quality by quality control staff. They are then moved into sealed curing chambers with a total capacity of 6,000 square meters. Climate units regulate humidity and temperature to achieve optimal strength development. Following curing, samples are tested in the laboratory, and compliant batches are released to the warehouse. Finished slabs are automatically palletized, wrapped, labeled, and stored for shipment. Customers can view the full range of exclusive paving products at the company's showroom, supported by professional consultation. The vast demolding line is an industrial-grade system engineered for the controlled extraction of concrete products from steel or plastic molds. It is designed for use in the production of vibro-pressed elements such as hollow blocks, paving slabs, curbstones, and related components. The line incorporates a rigid welded steel frame to ensure structural stability under continuous cyclic loading. The demolding process is executed by synchronized hydraulic and vibration units, calibrated to minimize residual stresses in the product and to prevent edge chipping or microcracking. Adjustable vibration frequency and amplitude allow adaptation to varying product geometries and concrete mix designs. Mold handling is facilitated through mechanical or robotic transfer systems, enabling precise positioning during the stripping cycle. The modular construction permits integration with conveyor lines, curing racks, and automated stacking devices. Control of the system is achieved via a programmable logic controller, PLC, with operator interface, providing parameter adjustment, cycle monitoring, and fault diagnostics. All mechanical components are manufactured from wear-resistant materials to increase service life, while maintenance access points are designed for rapid replacement of critical parts. The vast demolding line ensures dimensional accuracy, repeatability of process parameters, and high throughput, meeting industrial standards for precast concrete production. BRAER is one of the largest brick manufacturers in Russia, producing over 140 million units annually. Its famous Bavarian brick, known for its unique gradient coloring from red to dark brown, is created not with chemical pigments, but through a special firing technique. The process begins at the Abremskoye clay deposit near Tula, where 200,000 tons of clay are extracted annually. This clay is rich in iron oxide, which imparts the characteristic terracotta shades. Samples from each new batch are tested in the factory's laboratory, where miniature prototypes are shaped and fired. These tests predict the properties of full-scale production years in advance. Raw clay first passes through receiving shafts that crush large lumps, then travels 2 kilometers by conveyor through multiple treatment stages. Impurities are removed, and giant grinding mills with 20-ton millstones reduce the clay to a fine powder-like mass called schichte. Each sector of schichte storage is assigned to a specific product type. For Bavarian brick, the schichte is mixed with water in vertical mixers, creating a plastic mass resembling dough. The prepared mix enters the press, designed like an industrial extruder. It forces the mass through a die, forming a continuous clay column, which is then cut into segments containing 36 standard-size bricks. These raw bricks remain too moist and must be dried. They are loaded into large drying chambers the size of a 3-story building, where temperature and humidity are carefully controlled. After 48 hours, the dried bricks proceed to firing. The plant operates one of the longest kilns in Europe, measuring 204 meters and capable of holding over 500,000 bricks simultaneously. During standard firing, iron in the clay oxidizes, producing red coloration. For the Bavarian effect, a controlled flash firing introduces excess gas, triggering partial reduction of iron oxide. This creates irregular shading from bright red to deep brown. After about 2 days, finished bricks emerge and undergo quality testing. Mechanical tests confirm compressive strength up to 200 kilograms per square centimeter, allowing use in buildings over 10 stories high. Robotic systems then mix bricks from different batches to create natural shade variations. In packaging, layers of bricks are separated by paper, strapped, shrink-wrapped, and moved to storage. From there, Bavarian bricks are shipped across Russia and abroad. Produced from fire, water, and clay with modern technology, BRAER bricks preserve ancient tradition while offering exceptional strength and timeless aesthetics. Replacing the waterproofing system of an industrial roof requires precise coordination, technical expertise, and efficient execution, especially on a large scale. VJF Engineering recently completed such a challenge with the successful replacement of the entire roofing hydro-insulation system at the Sokotab tobacco processing plant in Radanovo, Plovdiv province. The project covered an impressive area of 12,000 square meters and was completed in just 12 days. A workforce of 38 people, including 34 skilled workers and 4 technical supervisors, was fully dedicated to the task. It all started with the removal, transport, and proper disposal of approximately 900 cubic meters of outdated insulation and membrane materials. To maintain safety standards, a 200-meter protective safety line was installed around the roof's perimeter before work began. The replacement system included the delivery and installation of 12,000 square meters of mineral wool insulation, totaling around 1,900 cubic meters in volume. For waterproofing, the team applied the Everguard TPO synthetic membrane, manufactured by the reputable US-based company GOE. Known for its high durability, UV resistance, and long-term performance, this membrane was an ideal solution for the industrial facility's roofing needs. In addition to the insulation and membrane work, the team also carried out specialized detailing tasks. These included the treatment of 185 meters of built-in gutters and the installation of 540 meters of TPO walkway rolls to ensure safe footpaths for rooftop access. The project also involved the careful dismantling and reinstallation of 14 linear roof lights. This project reflects VJF Engineering's ability to deliver high-performance roofing systems using modern materials and optimize work processes, all while maintaining strict timelines and safety regulations. It stands as a model of effective industrial roof renovation, meeting both structural and environmental performance goals.
The Liebherr LTM 1750 is more than a mobile crane. It is a symbol of controlled power, precision, and confidence on the job site. Built to handle the heaviest lifts with absolute authority, this 750-ton class crane stands as one of the most capable all-terrain lifting machines ever engineered. At first sight, the LTM 1750 commands attention with its long telescopic boom, massive carrier, and unmistakable presence. Yet its true strength lies beyond its size. The crane is designed to move, assemble, and lift with remarkable efficiency, combining mobility and performance in a way few machines can achieve. Whether navigating narrow access roads or setting up on complex industrial sites, it adapts with calm determination. The telescopic boom system is the heart of the machine. Extending to impressive lengths and supported by lattice jib options, it allows the LTM 1750 to reach extreme heights while maintaining lifting accuracy. Every extension feels deliberate, every movement smooth and controlled, even when handling loads that push the limits of conventional cranes. Advanced control systems continuously calculate load data, wind conditions, and stability, giving the operator confidence at every moment. Operating the LTM 1750 is an experience of trust. The operator sits high above the ground, surrounded by digital displays and intuitive controls, feeling the machine respond instantly to the smallest input. On major infrastructure projects, wind farms, refineries, and heavy industrial installations, the LTM 1750 becomes the backbone of the operation. It lifts turbine components toward the sky, positions bridge sections with millimeter accuracy, and supports construction schedules that depend on flawless execution. The LTM 1750 is not just about lifting weight. It represents human ambition made mechanical, turning planning, engineering, and courage into motion. When it works, everything else seems to fall into place, lifted quietly and decisively toward completion. Modern rail installation has evolved into a highly efficient, mechanized process where tasks that once required large crews can now be performed by just 2 skilled operators. Advanced rail laying systems integrate lifting, positioning, and alignment functions into compact, precisely controlled equipment, dramatically reducing manual labor while increasing accuracy and safety. Rails are delivered pre-aligned along the track corridor and handled using hydraulic manipulators that lift and place each rail segment with millimeter-level precision. One operator controls the positioning system while the second oversees alignment, fastening, and quality checks. Automated clamps and guided rollers ensure the rail is seated correctly on sleepers, maintaining the designed gauge, cant, and longitudinal alignment. Digital measurement tools continuously verify geometry, allowing immediate adjustments before permanent fastening. This approach minimizes rework, shortens installation time, and reduces physical strain on workers. By combining mechanization, smart tooling, and streamlined workflows, modern rail laying achieves higher productivity, consistent quality, and improved workplace safety, demonstrating how infrastructure construction continues to advance through engineering innovation. An underwater cat excavator is a highly specialized piece of heavy equipment engineered to perform excavation and material handling tasks in fully submerged environments where conventional machinery cannot operate. These machines are commonly deployed for harbor dredging, riverbed cleaning, dam maintenance, pipeline installation, bridge foundation works, and coastal engineering projects. The base platform is typically a standard Caterpillar hydraulic excavator that has been extensively modified for underwater operations. Key adaptations include a fully sealed powertrain, pressure-resistant hydraulic systems, corrosion-protected components, and specialized underwater lubrication. Critical elements such as the engine air intake, exhaust system, and electronic control units are either sealed or relocated above water using snorkel systems or umbilical connections. Hydraulic systems are the core of underwater performance. All hoses, fittings, and cylinders are designed to withstand hydrostatic pressure while preventing water ingress and oil leakage. Biodegradable hydraulic fluids are often used to minimize environmental impact in sensitive aquatic zones. Cooling systems are adapted to operate efficiently despite reduced airflow, frequently relying on water-to-oil heat exchangers. Operator control is managed either from a waterproof, pressurized cab or via remote control systems positioned on a support vessel or shoreline. High-definition underwater cameras, sonar sensors, and real-time telemetry provide the operator with continuous visibility and precise control, even in zero-visibility conditions caused by turbidity or sediment disturbance. The excavator's undercarriage is reinforced to maintain stability on uneven or soft seabeds. Depending on the application, standard tracks may be replaced or supplemented with wide track shoes, pontoons, or spud systems to distribute weight and prevent excessive sinking. Working depths can range from shallow waters to 20 meters or more, depending on configuration. Attachments are equally specialized. Buckets, grapples, cutters, and dredging tools are fabricated from abrasion-resistant steel and optimized for underwater cutting and scooping forces. Quick coupler systems allow rapid tool changes without surfacing the machine. From a technical perspective, underwater cat excavators represent a fusion of hydraulic engineering, marine technology, and heavy construction design. Their ability to operate continuously below the surface significantly reduces reliance on divers, improves safety, and increases productivity in complex marine construction environments.
This canal section gets rebuilt underwater, overturning the idea that groundwater makes restoration impossible with the Incomat mattress system. The Incomat mattress system takes over where conventional repair fails, allowing underwater concreting to stabilize the canal without draining it. A long laying unit, extended beyond 40 meters with excavators, is positioned to match the canal's cross profile. That platform stretching across the channel looks like it's carrying more than just equipment, it's holding the whole plan together. Ramps alone weigh around 40 tons, rising to 60 tons during placement. Mattresses are spread across the unit, then pulled precisely into the canal bed. Concrete fills them underwater, locking each section in place. Hydraulic steering keeps alignment centered through curved sections. Seeing heavy material settle so steadily underwater feels almost unreal. Which part of the vertical battery formwork actually determines how air moves inside these concrete ventilation blocks? Panels are arranged in a tight series, creating multiple casting chambers aligned side by side. Reinforcement is positioned into each cavity, setting the internal layout that defines airflow paths later on. Those narrow spaces don't look like much, but they decide how air will move through an entire building. Concrete is introduced into the vertical molds, filling each section evenly under controlled conditions. Damaged pavement disappears without being removed, as the infrared asphalt patching system rebuilds it using the same material. Heat is applied across the repair zone until the existing asphalt softens evenly, allowing it to be reshaped instead of discarded. This approach keeps the base layer intact while preparing it for blending. Seeing a rigid surface give in like that feels unexpectedly smooth. Once workable, the loosened asphalt is raked and redistributed to regain uniform density. Fresh mix is added only where gaps or loss have occurred, then integrated directly into the reheated layer. The surface is leveled to match surrounding pavement, preventing visible transitions. Compaction follows, binding the old and new material into a continuous structure. You might pause for a second trying to spot the original damage line. The method limits waste, reduces transport needs, and maintains structural continuity by treating the pavement as a reusable resource rather than debris. Heating remains controlled to avoid overheating the binder within the asphalt. The repair zone stays confined, preventing impact on nearby intact pavement. Equipment positioning ensures even heat distribution across the working area. Each pass reinforces consistency across the repaired section. The restored surface supports traffic without introducing weak joints. See how shaft construction equipment for heavy load transport enables vertical movement of heavy machinery inside deep shafts. Two vertical shafts reaching 100 meters deep rely on shaft construction equipment for heavy load transport to handle machines weighing up to 40 tons. Excavation progresses downward to form shafts with diameters of 8 and 14 meters, creating space for structural installation. That drop looks demanding, yet every section lines up with purpose. Once depth is achieved, shaft lining stabilizes the walls to support long-term use. Transport systems are then assembled inside, allowing heavy equipment to move vertically through the confined space. Each component is positioned to maintain balance during lifting and lowering operations. The longer the pipeline extends, the more precise alignment becomes with the Edna pipeline system. A 36-inch line stretches across 50 miles in just 3 months, and the Edna pipeline system keeps every welded section aligned. A 36-inch line stretches across 50 miles in just 3 months, and the Edna pipeline system keeps every welded section aligned. Welding units connect each section, building a sealed structure capable of handling internal flow demands. Coating follows to protect the exterior surface, then segments are lowered into the trench with controlled positioning. Backfilling secures the pipeline in place, completing the installation. The raw sand looks unusable, but the micrograder F70D is actually refining it into high-grade glass material. Watch silica sand shift from cloudy mixture to clean grains. Feed material enters the system and passes through shear clean scrubbing, breaking surface coatings and releasing impurities. That cloudy mix at this stage barely hints at the clarity expected later. The flow then moves into precision fine screening, where particles are classified by size, with oversize above 600 microns separated out. Heavy minerals are removed to refine purity further, tightening control over final composition. Water circulates through the process, with up to 95% recovered for reuse, keeping operations contained. The clean sand exits with consistent grading, meeting glass and foundry requirements, while minimizing waste discharge. A steel pipeline gains its outer strength not from the metal itself, but from the thick layer applied by the external pipeline concrete coating (CWC) system. Pipe sections are prepared and aligned before entering the coating stage, ensuring surfaces are ready for bonding. The coating material is applied around the pipe exterior, forming a dense protective layer designed to resist mechanical impact and environmental stress. The applied concrete is shaped evenly along the pipe surface to maintain consistent thickness. Rotation keeps distribution uniform during placement, preventing imbalance along the length. You catch yourself wondering how that added weight stays so controlled during movement. The coated pipes move through curing, allowing the outer layer to harden and lock into place. Handling systems then position each section for transport or installation. The result is a reinforced pipeline capable of withstanding external loads while maintaining internal flow conditions. A 2,009-meter span stands above a canyon, while suspension bridge construction systems assemble steel truss sections in midair, linking both sides through cables and lifted segments. That gap below changes everything. Concrete piles fail underground more often from slight misalignment than from lack of strength, and D51 piling rig exists to prevent that hidden problem. The machine positions itself over marked points, aligning its mast vertically before any pile enters the ground. A reference line is checked against the mast to confirm true vertical before driving continues. Hydraulic force drives the pile downward in a controlled motion, keeping the path straight through varying soil resistance. That steady descent hides how much correction is happening moment by moment. Operators monitor verticality closely, adjusting the mast angle to keep deviation within strict limits. Connection joints between pile sections are secured to maintain continuity and load transfer along the full length. Additional pile sections are joined as depth increases, extending the column deeper below the surface. Feels like feeding segments into the earth while trying to keep an invisible line perfectly straight. The rig maintains pressure and alignment until the required depth is reached. Once complete, the pile remains embedded as a stable structural base. One small tilt up top could shift everything down below. Final depth readings are verified to confirm the pile meets structural design requirements. Each placement builds part of a larger foundation grid. You realize how much depends on something you'll never see again, once buried. Could a borehole drilling rig really create a stable water supply system beneath a concrete floor? The borehole drilling rig is positioned within the building, aligning its drilling axis before penetrating the surface. Rotary drilling advances downward, breaking soil and rock while removing cuttings through continuous circulation. That confined space makes every movement feel tighter than expected. Operators guide the drill path to maintain vertical alignment despite changing resistance below. Drill rods are added section by section to extend depth as the borehole progresses. Feels like the machine is quietly opening a path where none existed a moment ago. Once the target depth is reached, casing is installed to stabilize the well walls. A pumping system is then fitted to complete the water supply setup. The finished borehole delivers a reliable underground water source for daily use. This two-component bitumen coating blocks water in places where seepage once spread unnoticed. Material arrives as a modified bitumen emulsion with an added accelerator, prepared to react quickly after mixing. Workers combine the components until the blend reaches a thick, spreadable consistency, suited for vertical and horizontal areas. That texture decides how the layer grips uneven surfaces, rather than how it looks. The coating is then applied directly onto concrete or masonry, forming a continuous layer without joints. The thixotropic behavior keeps the material from sliding, allowing it to stay in place while curing progresses. Feels like spreading something that refuses to run, no matter how the surface tilts. Application continues across corners and edges, where weak points usually form. Each pass overlaps slightly, ensuring no gaps remain in the membrane. The accelerator shortens waiting time, so the surface firms up while maintaining flexibility. A slight delay here opens a path for water later, and that consequence stays hidden until it's too late. Once cured, the coating resists moisture from both inside and outside exposure. The final layer bonds tightly, creating a seamless waterproof shield across the structure. Water entering freely upstream ends up confined into pressurized flow inside the hydropower turbine system, masking how force is reshaped before electricity emerges from turbines and generators feeding transmission lines. That shift feels tighter than expected. The smooth tunnel floor looks effortless, but invert concrete is actively shaping every section underneath. Concrete is delivered into the tunnel section and directed along the invert, filling the lowest structural layer. Workers guide the flow to match the required profile, forming a stable base for the structure above. That surface only looks natural once everything is pressed into place against rough ground. After the invert concrete settles, side walkways are formed along both edges of the tunnel. Feels like carving a straight path inside a space that resists staying straight. Placement continues section by section as equipment advances through the tunnel. Each segment repeats the same sequence of filling and shaping. One deviation here would travel forward through every section that follows. The result is a continuous internal base ready for further tunnel systems. People once depended on rainfall, but this canal system now provides controlled irrigation across wide farmland areas. Fields breathe again. Lightweight aerated concrete using a lightweight concrete mixer changes how blocks are produced for thermal insulation. Raw materials including cement, limestone, fly ash, and aluminum powder are measured and blended with water into a fluid mix. That fine aluminum reaction quietly creates air bubbles inside the slurry. The mixture expands and thickens, forming a porous structure before setting. Feels like bread dough rising, except this one builds walls. The material is poured into molds or directed into block shapes. After curing without autoclaving, the blocks gain strength while staying light. Weight drops, yet structural performance holds steady. Density control adjusts insulation and load capacity for different construction needs. A diaphragm wall formed by diaphragm wall trenching equipment often carries the entire load of a future structure before anything rises above ground. Load transfer through the wall begins as soon as the concrete gains strength underground. The trench is already formed and supported by slurry, visible as a narrow, open slot along the ground. Slurry density is maintained within a controlled range to keep trench walls stable. That open gap holds its shape purely because of fluid pressure, not solid support. Hydrostatic balance between slurry and surrounding soil prevents collapse. A crane positions the tremie system above the trench, aligning it vertically before discharge. Vertical alignment ensures uniform concrete distribution along the panel depth. Concrete flows downward through the pipe, entering from the bottom and forcing slurry upward. The tremie outlet remains embedded in fresh concrete during placement. The exchange happens underground, hidden yet critical to the final structure. Workers guide the process from the surface, monitoring flow and position. Flow consistency is checked continuously during discharge. A dump truck supplies fresh concrete, feeding the hopper continuously. Supply timing is coordinated to avoid interruption in the pour. Feels like pouring into a space that refuses to reveal its depth. The fill level rises steadily inside the trench. Concrete level is tracked relative to trench depth throughout placement. Once the section reaches the required height, the pour stops, leaving a solid wall panel below. Everything above still looks temporary, but the real structure is already locked in place. Two yellow hoppers at the front feed concrete directly into the excavation trench. Hopper openings regulate the volume entering the tremie system. A crane holds the pouring assembly in position, lowering it precisely to the target point. Position control keeps the tremie centered within the trench. Below, a deep trench remains open, stabilized by circulating slurry that supports the walls. Continuous circulation maintains uniform slurry properties. Behind the setup, a slurry treatment unit processes and recycles the fluid to maintain consistent conditions. Separated solids are removed during slurry processing cycles. Workers monitor the flow rate and adjust positioning to keep the pour steady. This stage carries out bottom-up concrete placement using a tremie pipe. Placement sequence follows strict control to maintain structural integrity. The pipe extends to the base of the trench, allowing concrete to enter from below. As concrete rises, it pushes the slurry upward and out of the trench. This controlled displacement prevents mixing, ensuring a dense and continuous wall structure forms underground. Follow this sequence to see how machines in coordination remove an entire bridge safely. It's fascinating how calculated forces can dismantle thousands of tons without losing control. Concrete cracks under hydraulic hammers and wrecking balls, yet every machine moves with purpose. Seeing these massive spans collapse section by section is unexpectedly gripping. As the bridge is segmented, excavators lift debris and cranes stabilize loose sections, keeping the work area safe. Workers guide machinery through tight spaces, monitoring stress points and using hydraulic shears to cut steel reinforcements. Every concrete block, every twisted beam is handled in a deliberate sequence. The orchestration of machines here is tighter than it appears. Rubble is sorted into piles for transport, while the terrain is prepared for future construction. Demolition exposes hidden layers of engineering inside the bridge, showing how supports and reinforcements interacted to maintain structural integrity for decades. Cranes, excavators, and operators synchronize every movement with minimal margin for error, proving that careful planning outweighs sheer force in large-scale demolition. By the end, the old Volmarstein Bridge is fully removed, leaving the site ready for a new bridge installation. Watching an entire bridge vanish piece by piece is quietly thrilling. Observing teams maneuver heavy equipment around unstable debris highlights human skill paired with engineering. Deep underground, controlled blasts break through rock as jumbo and winder operators guide the workflow. Drill and blast engineers coordinate each shot with precision. Service crews maintain equipment and assist miners during shifts. Every tunnel emerges from exact timing and teamwork, and watching the rock split reminds you of the hidden effort behind every meter mined. The layers of shotcrete pile up in ways that almost defy gravity, yet each one clings to the bench exactly where it should. The nozzle man manipulates wet mix with a skill that seems impossible to predict, adjusting angles and distances so the material envelops the steel bars without covering them entirely. The subtle interplay between bench angle and material flow decides the stability of the wall, not brute force. After the bench is formed at roughly 45 degrees, the next layers are applied perpendicular to prevent skipping or rolling. Notice how the shot creeps from behind the bars instead of building up on the front. Every deformation remains visible until it's fully encased. Maintaining that perfect surface requires constant adjustments. Even small miscalculations here can affect the entire panel's integrity. The technique transforms chaotic wet mix into a stable, layered structure. Watching this makes you realize how human judgment directly orchestrates the cohesion of concrete layers. The dock crane positions massive piles with pinpoint accuracy, deciding the stability of the new cruise terminal pier. The vessel positions each pile with exacting precision, guided by the jacket pontoon that stabilizes the setup against dynamic marine conditions. Operators continuously adjust both the swing angle and vertical alignment of every pile, working in close coordination with the terminal team on shore. Each pile is lowered into predetermined locations, forming the reinforced concrete foundation that will eventually support large vessels docking. After the first set of piles is driven, subsequent layers are added carefully. The bench system allows new piles to wrap around previously placed ones at consistent angles, preventing material from accumulating at the front. Operators monitor real-time alignment data from visual and electronic guides on the quay, verifying depth, tilt, and orientation. As construction progresses, the quay rises gradually above water level. Piles are frequently checked to avoid cumulative errors that could weaken the structure. Each swing of the 550 vessel is synchronized with pontoon adjustments, ensuring smooth force transmission and accurate pile placement. Misalignment is mitigated through repeated minor corrections, and material wraps around the bars cleanly, preserving the intended structural form. The final structure relies on each pile's position, angle, and depth. The vessel's sheer power, combined with pontoon stabilization and crew skill, ensures the quay can withstand high tides, waves, and the weight of docking ships. By the last swings, the quay emerges fully formed, each pile aligned perfectly, creating a robust platform ready for heavy-duty maritime use. Throughout the operation, the crew maintains constant communication, adapting quickly to any shifts in weather or water currents. Adjustments to the swing speed and pile angle are critical to prevent overdriving or misalignment. Incredible how the coordination between vessel, pontoon, and crew keeps everything under control despite the immense forces at play. Throughout the operation, the crew maintains constant communication, adapting quickly to any shifts in weather or water currents. Adjustments to the swing speed and pile angle are critical to prevent overdriving or misalignment. Incredible how the coordination between vessel, pontoon, and crew keeps everything under control despite the immense forces at play.
Situated at the narrow waist of the American continent, Panama has long served as a strategic gateway for global transit. At the heart of this role stands the Panama Canal, a 20th-century engineering landmark that, since its opening in 1914, has enabled efficient maritime passage between the Atlantic and Pacific Oceans. To meet the demands of modern global trade, a major expansion program was launched to add a third transit lane capable of accommodating post-Panamax vessels. By August 2013, overall progress of the expansion had reached approximately 62%, supported by an investment of $5.25 billion United States dollars. Channel widening and deepening works on both the Atlantic and Pacific entrances were completed, while navigation improvements in Gatun Lake and the Culebra Cut approached their final stages. These efforts required the deployment of a wide range of advanced dredging equipment operating throughout the waterway. The centerpiece of the expansion is the third set of locks, consisting of two new lock complexes with chambers 30% larger than the original locks. Each chamber incorporates 3 water-saving basins, allowing up to 60% of the water used in each transit to be reused, significantly improving operational sustainability. Water flow is controlled by a sophisticated valve system manufactured in South Korea, while massive rolling steel gates, each weighing approximately 300 tons, are being fabricated in Italy. On the Pacific side, a 6.1-kilometer exclusive access channel is under construction, including a dam designed to manage a 9-meter water level difference with Lake Miraflores. In parallel, projects to raise Gatun Lake's operational level, large-scale reforestation, wildlife relocation, and archaeological research underscore the expansion's integrated engineering, environmental, and cultural approach. The Panama Canal expansion marks the creation of a new chapter in global maritime history, driven by technical precision, responsibility, and long-term vision. Day and night, the Panama Canal remains in constant motion, guiding vessels from north to south and from south to north, sustaining global maritime trade without interruption. To preserve this role and meet the demands of modern shipping, the Panama Canal expansion program was launched as the most ambitious infrastructure undertaking in the nation's history. By mid-2014, nearly 3/4 of the expansion had been completed. More than 35,000 engineers, technicians, and skilled workers applied advanced engineering practices under intense tropical conditions. At the heart of the program stands the construction of the new lock complexes, wider, deeper, and longer than the original locks, representing the most valuable and technically complex component of the entire expansion. Across the Atlantic and Pacific sites, over 3 million cubic meters of concrete had been placed, while nearly 38 million cubic meters of earth and rock were excavated and relocated. In the Pacific sector, dense basalt rock was extracted and processed into high-quality aggregate, forming the structural backbone of the new lock chambers. A dedicated industrial park was established to crush rock, fabricate steel, and maintain heavy construction equipment, ensuring uninterrupted progress. Logistics operate on a monumental scale. Each week, barges transport tens of thousands of tons of basalt over long distances to sustain concrete production. Meanwhile, massive steel lock gates, each weighing approximately 300 tons, are manufactured overseas and delivered to Panama. Their arrival signals the transition into the electromechanical phase, including the installation of advanced hydraulic valve systems that precisely control water movement between chambers, lakes, and water-saving basins. Beyond the locks, extensive dredging continues at the canal entrances, Gatun Lake, and the historic Culebra Cut, where channels are widened, deepened, and realigned. Environmental stewardship remains integral, with reforestation, wildlife relocation, and archaeological discoveries embedded into every phase. This expansion reshapes a global passage, securing the Panama Canal's role as a strategic link between oceans for generations to come. Construction of the third set of locks on the Atlantic side advances steadily, with major civil works completed and large-scale concrete placement shaping the chambers. Installation of electromechanical systems and massive steel gates marks a critical phase toward enabling post-Panamax vessel transit. Nearly a century after its original completion, the Panama Canal entered a new era through one of the most ambitious infrastructure programs ever undertaken in the maritime sector. Launched in 2007, the Panama Canal Expansion Project was designed to secure the waterway's long-term competitiveness by enabling the transit of post-Panamax vessels and responding to the rapid growth of global trade. With an investment of approximately $5.25 billion United States dollars and an 8-year execution period, the program encompassed large-scale dredging of the Atlantic and Pacific entrances, Gatun Lake, and the Culebra Cut. Navigational channels were widened and deepened to accommodate vessels with drafts of up to 50 feet, while Gatun Lake's maximum operating level was raised by 45 centimeters to strengthen water supply reliability. A key component was the excavation of a new Pacific access channel, extending 6.1 kilometers and requiring the removal of nearly 50 million cubic meters of material. This effort included the construction of the 2.3-kilometer Borinquin Dam, allowing controlled water separation and channel operation above lake level. In parallel, high-capacity dredging equipment, including some of the most powerful dredges in the world, was deployed to meet unprecedented excavation demands. The centerpiece of the expansion was the construction of the third set of locks on both oceans. These massive structures feature 55-meter-wide chambers and rolling gates weighing up to 700 tons each. Dedicated industrial parks on the Atlantic and Pacific sides produced over 4.8 million cubic meters of concrete to support lock construction. Beyond engineering, the project integrated environmental management, including reforestation of more than 200 hectares and the protection of archaeological and paleontological discoveries. Upon completion, the expanded Panama Canal emerged as a global benchmark in large-scale civil engineering, transforming international shipping and reinforcing its role as a strategic corridor between oceans. The construction of the Panama Canal expansion represents a landmark engineering achievement, enabling post-Panamax transit through new locks, deeper channels, advanced water management systems, and enhanced global maritime connectivity. Transit through the Panama Canal follows a standardized process for all vessels, from sailboats to large cruise ships. Ships enter lock chambers through massive gates, water levels are raised in about 8 minutes, and locomotives keep vessels centered. An ocean-to-ocean transit takes 8 to 10 hours. The Panama Canal is the only waterway in the world that uses locomotives to guide vessels safely through Panamax locks. Regular preventive and major maintenance is carried out at the Pedro Miguel Lock workshops, where systems are inspected, disassembled, tested, and restored to ensure reliability, safety, and long service life. What do a cableway excavator, a turntable, and a synchrolift have in common? Though rarely seen, each plays a critical role in keeping the Panama Canal operating without interruption. The cableway excavator removes vegetation from the Chagres River to protect navigation routes. The Gatun turntable rotates locomotives, handling heavy loads with speed and precision. The synchrolift hydraulically raises floating equipment for maintenance. Quietly, these systems ensure continuous, safe canal operations.